faithfully delivering value and exploring great books from around the world. Hi, this is Sally here with the Book Talk. Today's book for interpretation is Following the Starlings in Flight. The character Leon, for Starlings, has the wood radical and Jing, like in Beijing. It's a small sparrow-like bird, famous for its metallic feathers. But even though the book has starlings in the title, it's not a science book about birds. The book also has a subtitle, The Wonderland of Complex Systems, where complex systems are the main topic. Starlings have a close relationship with complex systems. As social birds, starlings fly in flocks of hundreds or thousands. It's not random. Flocking is key to their survival. For instance, starlings use the flock's power to fend off predators. A starling flock is a prime complex system, and studying them is the hallmark work of author Giorgio Parisi. Parisi is an Italian physicist and professor at the University of Rome. At 74, he's an academic heavyweight. In 2021, he won the Nobel Prize in Physics for his work on complex systems. In Following the Starlings in Flight, Parisi shares his complex systems research in easy-to-understand terms. The book was highly praised when it came out. Renowned scientist Juan Weigong said, "This book is more intriguing than a mystery novel." What's more, Parisi genuinely shares lessons from his decades in research, like how to find inspiration even if you're not in the field. Hearing this top scholar's heartfelt insights will be very beneficial. This talk is split into two parts. First, an intro to Parisi's research achievements. Then, we'll talk about the author's personal insights from his research career. Okay, let's start by following this physics master on our journey through the complex world. First up, Parisi's research, where his key contribution is developing theories for complex systems. This part might be challenging with some technical terms. We'll add essential background info as we go. A complex system is one where basic units interact under rules, showing complex group behavior. In the real world, complex systems are everywhere. For instance, in physics, atoms or electrons, their individual motion rules are super simple, but when you put them together, they create all kinds of wild scientific phenomena. Well, why does liquid boil? Why magnets have magnetism, and so on. All these are complex behaviors from particles inside matter. On a macro scale, it's not just physics. Fields with lots of people involved also show traits of complex systems, like in finance. Traders' buy-sell actions can lead to totally unpredictable market outcomes. In complex systems, Parisi himself is most proud of two works, Observing Starlings and Studying Spin Glass. We'll now dive into one key achievement. By watching starlings, he uncovered patterns in flock behavior. Every winter, huge flocks of starlings migrate from northern Europe to Italy for the cold months. The massive starling flocks always swirl in Rome's skies, and this size gives him new abilities. For example, when starlings dodge predators, they show all sorts of cool phenomena. One of their predators is a bird called the peregrine falcon. It's a raptor with a wingspan up to a meter. When diving full speed, they can hit 200 kilometers per hour. A lone starling can't defend against a falcon attack, but a whole flock gains the power to fight back. If a falcon charges the flock, starlings quickly close ranks, gather hundreds together, and coordinate to dodge attacks. Against this massive formation, the falcon often can't find a way in. Show that if it recklessly flies in, the falcon might crash into a starling and get hurt or fall. But amazingly, in these complex, shifting formations, the starlings stay orderly, never colliding with each other. All this totally fascinated Parisi, and he wanted to figure out what rules these flocks follow in flight. To study starlings, Parisi's first big challenge was how to clearly see the flock's movement paths in the air. Oh, you can easily find tons of starling flight pics or videos online, but that's nowhere near enough. What Parisi wanted was precise 3D flight data of starling flocks, so he needed better filming gear and a tighter setup. Parisi used to work in theoretical physics, dealing with concepts and equations. He rarely got involved in experiment design. But this time, to capture starlings' exact flight patterns, he threw himself into it completely. Oh, in the filming process, From optimizing cameras to finding perfect angles, storing massive images to coding analysis programs, every detail mattered. Countless details needed repeated tweaking by Parisi and his team during the Starling experiments. As the author put it, armchair theorists never realize how many battlefield problems they'd face. It was this all-out, no detail, too small dedication. After 2 years of observation, Parisi's team built the world's first 3D database of starling flocks. They even created algorithms to track thousands of birds across hundreds of high-res photos, pinpointing each turn within hundredths of a second. With this rich raw data, the next step was Parisi's sweet spot: statistical analysis of massive data sets. Through Parisi's analysis, they found many flight patterns, like how flocks seem to shrink and grow super fast when watched with the naked eye. A flock compresses from huge to tiny in an instant. Using 3D imaging, Parisi discovered this illusion happens because starling formations aren't spheres, they're flat disks. Imagine a big round plate. Face on, it looks large. But tilt your view slightly, and it appears small and flat. Same with starling flocks. Their disc shape makes size shifts seem lightning fast. Another shocker. Birds at the flock's edge were nearly 1/3 denser than those at the center. So in starling flocks, it's sparser at the center but more crowded toward the edges. People used to think density would be higher at the center. After all, the deeper in, the farther from danger. But experiments overturned that idea. Parisi found this actually helps fend off predators. A lone bird is easy prey, but edge birds stay tight, hard for falcons to catch. With outer protection, center birds stay safe without overcrowding. Beyond these findings, the biggest breakthrough was understanding how flocks coordinate. How do they sync up during flight? First, starlings maintain unique spacing patterns when flying together. Specifically, each bird keeps more space front-back but stays closer side to side. This pattern holds in both dense and sparse flocks. It's independent of overall density.
Parisi concluded this alignment helps birds avoid collisions while maintaining position awareness.
It's like highway driving. Cars keep just meters apart sideways, but dozens of meters front and back. Building on this, Parisi analyzed how starlings adjust flight paths midair. To quantify this, his team introduced the term anisotropy. Originally from physics, it describes how material properties vary by direction. Applied to flocks, greater anisotropy means birds' flight paths influence each other more. Zero anisotropy, no coordination, they'd fly independently. As a physicist, Parisi first assumed individual movement depended purely on absolute distance to neighbors. After all, Newton's gravity law states attraction inversely relates to distance squared. So they measured the flocks. In the images, anisotropy between bird pairs showed. Closer birds had high anisotropy, while distant ones had low values. This matched Parisi's initial guess, but new data quickly overturned this idea. When comparing flocks, researchers found starlings 2 meters apart could have huge anisotropy in one group, yet almost zero in another at the same distance. Faced with solid data, Parisi changed his original thinking. He stopped using absolute distance. Instead, he started focusing on relative positions. He patiently numbered each bird's neighbors. Neighbor 1, closest, neighbor 2, 3, and so on.
Calculations showed that regardless of flock size or density, anisotropy with neighbor 1 was consistently high.
Values decreased with neighbors 2 and 3, and by neighbor 7, anisotropy approached 0. So, thus, birds' movements depend not on absolute distance, but on their relative ranking. This principle isn't hard to grasp. Imagine running with friends. To stay in sync, you just match the pace of those nearest to you.
Based on these simple rules, each starling adjusts its speed and direction, using its closest companions.
During turns, a small group on one side initiates first, then the message spreads rapidly outward. Within moments, all birds turn in sequence. Even 1,000 bird flocks complete turns in just 1 second. While Parisi's findings seem simple, the real breakthrough was his innovative approach. It pioneered applying statistical physics to solve complex group behaviors in biology. By introducing quantifiable methods, it revolutionized how we study flocks, herds, and other animal groups. This work led to a widely cited paper by Parisi, now referenced in over 2,000 studies. Actually, long before Starlings, Parisi was already famous in disordered systems, all thanks to his breakthrough in spin glass research. Spin in spin glass refers to rotation. It's not actual glass, but a type of metal alloy. These alloys have wild magnetic properties. To understand spin glass deeper, we first need to discuss material magnetism. Generally, materials have two main magnetic states, ferromagnetic and antiferromagnetic. These states depend on the spin orientation of particles inside the material. Imagine spins as arrows. If all arrows point the same way, you get ferromagnetism. Like everyday magnets, classic ferromagnetic materials.
If adjacent particles have half up or half down arrows canceling out, that's antiferromagnetic.
But in spin glass, these arrow directions get messy. The key difference? In spin glass, each particle's spin is influenced by neighbors. So what's that like? The author uses a relatable analogy. Picture three people, A, B, C, in a drama. They must split into teams, each picking a side. If A and B get along but C hates both, they naturally form two teams.
But what if all three dislike each other?
When grouping, one team will have two who dislike each other, creating frustration. In spin glass, each of three particles tries to influence neighbors' spins. Friendship here means spins align, attractive force, spin oppose, repulsive force, and this is just three particles. Now imagine millions of particles, some friendly, some hostile. These interactions make team picking insanely complex. Every combo creates frustration, forcing constant adjustments. This means the magnetism produced by these particles keeps changing. How can we describe or analyze this change? That's what spin glass research is about. For Parisi, the key was finding the right mathematical solution. Coincidentally, while studying other problems, Parisi discovered a method to explain spin glass systems. This method is called the replica method. Re as in reproduction, plica as in original. The replica method copies a changing system multiple times, compares the replica's behaviors to uncover hidden patterns. After introducing it, Parisi's team merged the replica method with physics, creating a mathematical framework for spin glass. Parisi's key insight: disordered systems like spin glass can have multiple equilibrium states simultaneously. How to understand this? Take water. At certain temperatures or pressures, it's either liquid, solid, or gas. We'd say water is in one state or phase, but in special cases, water can be in two states. At 100 degrees Celsius, water can be both liquid and gas, what we call phase coexistence. But spin glass has countless phases at once due to complex spin interactions, creating unique magnetic properties. For example, spin glass has a property called magnetic relaxation. Relaxation, as in releasing tension. Many materials magnetize quickly under external magnetic fields. This happens almost instantly, but spin glass magnetizes much slower. Though it magnetizes, the process takes minutes or even hours. This happens because spin glass has multiple equilibrium states. Aligning them all is extremely difficult. Like organizing a chaotic group to move in one direction, it takes serious coordination time. Moreover, spin glass research methods apply to other systems too. Whether it's systems of atoms, molecules, or cells, this analytical approach applies. Even human societies are full of similar systems, where complex interactions between individuals create unique macro phenomena. All these can be analyzed using spin glass research methods. After covering Parisi's main research, let's discuss his insights on leveraging unconscious thinking for inspiration and intuition. It's not, if you work in research or creative fields, these tips from a Nobel laureate might prove invaluable. After decades in research, Parisi's key insight is mastering unconscious thinking.
Modern psychology defines unconscious as mental activities without active conscious involvement.
We sometimes hear subconscious, but that's mainly used in Freudian psychoanalysis. It's rarely used in mainstream academia today. So what is unconscious thinking? Typically, conscious thinking uses language to structure logic, like organizing thoughts with words. When chatting, the whole sentence emerges naturally after the first word. Even silent thinking uses internal language to connect concepts, like threading scattered ideas together. This is conscious thinking. Parisi calls it linguistic thinking, while unconscious thinking is non-linguistic, letting ideas flow freely without logical structuring. Currently, scientists still know little about this process. Parisi admits he's no expert, but believes this mode, while not logically organized, offers two benefits: sparking inspiration and cultivating intuition. Let's unpack this. Parisi suggests harnessing non-linguistic unconscious thinking boosts the odds of inspiration striking. So how exactly does this inspiration work? Parisi gives an example. In theoretical physics research, he often programs computers, but programs frequently produce wildly unexpected results. Parisi admits he's had countless experiences tinkering for hours without finding the bug, and he'd meticulously check every line of code, missing comma, typo, but errors kept popping up. At such times, he'd let go and just drive home. Yet halfway home, he'd suddenly spot the mistake, and sure enough, it was there. This sudden inspiration struck in his research projects too. He and colleagues once wrestled with an extremely tough problem. What exactly? Parisi doesn't specify, but recalls being stuck over a decade, nearly giving up. Then, at a conference lunch, casually mentioning it led him straight to the solution. The answer just surfaced like it floated up from deep water. These flashes of insight, Parisi believes they're non-linguistic thinking at work. Though consciously stopping work, his unconscious mind kept processing. We all face similar blocks in daily work. One bottleneck slowing everything down.
In such moments, Parisi says, let unconscious thinking step in.
His method: set the problem aside, let ideas percolate, solutions might bubble up spontaneously. Beyond inspiration, unconscious thinking also cultivates scientific intuition. You might wonder, aren't scientists hyper-rational? How can intuition play a role? Parisi's scientific intuition means breaking free from existing frameworks.
People imagine scientific progress as step-by-step bridge building.
This is classic linguistic thinking, step-by-step progression, with each link interlocking. But in reality, major scientific leaps are often sudden. Breakthroughs require breaking free from traditional constraints. To illustrate, Parisi cites quantum physics development, what he calls physics' greatest adventure. In the early 20th century, physics advanced rapidly, yet faced unsolvable puzzles. Like blackbody radiation, objects absorbing but not reflecting electromagnetic waves, yet constantly emitting them. Scientists found its energy emission bizarre. Discontinuous packets with wavelengths determined solely by temperature. Classical physics couldn't explain this, not due to incompetence, but needing quantum mechanics, which didn't exist yet. So what could be done? Most scholars patched classical theories, but some chose radical new paths. In 1900, Planck proposed energy quanta, clashing with classical physics. Despite skepticism, his fierce intuition insisted this solved blackbody radiation. While Planck's solution had gaps, it inspired decades of work culminating in quantum mechanics, finally solving the puzzle. Such intuition-driven breakthroughs fill scientific history. The book shares other examples too, like Einstein having similar experiences. In 1907, while pondering gravity, Einstein had a counterintuitive idea: gravity depends on the observer's frame of reference. Einstein himself called this the happiest thought of my life. This assumption became the foundation of his general relativity theory.
But intuition requires deep understanding of your work as a prerequisite.
As the book says, know your equipment, your system, your phenomena so well that correct answers come effortlessly. Only through thorough preparation can inspiration and intuition grace you. Ever had such inspired or intuitive moments yourself? Share your stories in the comments. Looking back on decades in science, Parisi feels profound gratitude for his career. To him, scientists build bonfires in darkness. More wood means brighter light. Each discovery adds fuel, illuminating humanity's unknowns. All right, that wraps up our journey through following the starlings in flight. Reading notes below the audio. See you next time.